Welcome, my name is Michael Johnson, and this is What is Your Bacon Number? An Introduction to Graph Databases. Before we begin, I'd like to take a moment to highlight a few things. As many of you know, PARS is a community-led organization dedicated to the upliftment of its members. PARS includes a number of opportunities, including local events, such as local user groups and SQL Saturdays, as well as online opportunities, such as PARS marathons and PARS virtual chapters. This year, a new professional membership has been added. This includes additional training and networking opportunities. If you'd like to find out more, head on over to pars.org. As we'd also like to ask that you provide us with feedback for both this talk as well as the event in general. Please visit the session evaluation link for more. A little bit more about myself. I'm the principal consultant at Cobalt Analytics, a BI and analytics consultancy based in Johannesburg, South Africa. I'm also a Microsoft Data Platform MVP and lead the PARS Business Analytics virtual chapter. But enough of that. Let's begin by looking at what we're going to be talking about today. I'd like to begin with a challenge. This challenge began in 1994 when the actor Kevin Bacon said during an interview that he had worked with everyone in Hollywood or someone who had worked with them. While this did not turn out to be accurate, it started a new game. This game would be called the Bacon Number, or the 6 degrees of Kevin Bacon, and this would involve finding the distance between any actor and Kevin Bacon. Here's how it works. We begin with Kevin Bacon himself. As Kevin Bacon is Kevin Bacon, there is no distance between him. Therefore, his Bacon number is 0. Next, we have Meryl Streep. In 1994, Meryl Streep acted in the movie The River Wild with Kevin Bacon. Meryl has therefore worked directly with Kevin, and her Bacon number is 1. Ian McKellen, on the other hand, has never worked directly with Kevin Bacon. He did, however, work on the film X-Men Days of Future Past. Also in the cast of this film was Michael Fassbender. Michael also worked on another film in this franchise, X-Men First Class, along with Kevin Bacon. This means that Michael Fassbender has a score of 1, and therefore Ian McKellen has a score of 2. During this talk, we're going to use graph databases to help us calculate the Bacon number of various actors. We will begin. So what are we going to look at today? We'll begin by looking at a graph database, as well as some of the history and many implementations. Then we will have a look at Cosmos DB. Cosmos DB is a multimodal database that includes an implementation of a graph database. With some of the theory out of the way, I'll show you how I modeled and loaded the content of the IMDb database into Cosmos DB. Next, we'll look at how we can query the graph to calculate the shortest path between any two actors. What is a graph database? In this section, we discuss some of the basic fundamentals behind a graph database. But before we begin, let's have a look at some of the other types of databases that exist. The simplest is the key value store. This type of database stores values using a unique ID for each value. This unique ID is then used to retrieve the value from the store. Because of the simple ID lookup and the fact that these types of databases are often memory bound, these type of databases can be lightning fast. Key value databases, such as Redis Cache, are often used for things like storing session state on large web server farms, such as those run by Facebook. The next type of database is a tabular database or a columnar database. These are simply large tables, where each entity is stored in a row, and each row is made up of multiple columns, where each column represents a property of the entity. Simple implementations of a tabular database could include things like Excel for small data, through to large implementations such as Cassandra and Google Bigtable. The next type of database is a document database. The most popular document database is probably MongoDB. Document databases have similarities to key value stores, except that they store more complex data types, usually in the form of a serialized JSON object. Unlike key value stores, documents can contain nested objects that model relationships between entities within the document, but not usually between documents. It is also possible to index attributes within the document, allowing for better document search and retrieval. Finally, there is the relational database. Relational databases are probably the most popular type of database used and support many advanced features such as a schema, constraints, and most importantly is a rich query language known as SQL. There are many popular implementations of the relational database, including MS SQL Server, Oracle, and MySQL Server. The challenge with these types of databases is that relationships are either non-existent or second-class citizens, and there comes times when the relationship between objects is sometimes more important than the data itself, and this is where graph databases fit in. Graph theory. Like relational databases, graph databases are also based on mathematics, and graph databases are based on graph theory. Graph theory was first introduced by Leonhard Euler, a Swiss mathematician living in Russia, and as with the Baker number, Euler was also looking to solve a problem. This problem was known as the 7 bridges of Königsberg. The problem was to find a path that would cross over each of the city's 7 bridges, without ever crossing any bridge more than once. Euler found that the paths through the city were of no relevance, only the land masses that you were on and the bridges that connected them. This allowed him to simplify the map of the city to a basic graph, consisting of vertices for the land masses and edges for the bridges. Using this simplified model and a few basic principles, Euler was able to deduce that there was no possible path through the city that would meet these criteria. It was from this that our brand new branch of mathematics was formed. Next we look at some of the basic principles of a graph. We saw a moment ago a graph consists of vertices and edges. A vertex, often called a node, represents an object in our model, and this object can be anything that you like. Although not required, graphs usually have more than one node, and between these nodes is a relationship called an edge. Graph databases are an implementation of a directed graph. This means that the relationships between the 2 nodes have a direction, and this direction will provide us with much needed context. Although the idea of a graph database is pretty simple, there are still many ways to implement a graph database. 2 of the most popular are the resource description framework and the labeled property graph. The resource description framework, or RDF for short, is based on the semantic web, something that was proposed by, amongst others, Tim Berners-Lee. If that name is familiar to you, that's probably because he was part of the team that brought us the internet. The RDF represents entities as a triple. This triple consists of a subject, an object, and a predicate. If you return to our example of Kevin Bacon acting in the film The River Wild, then this is what it would look like. We would begin with a subject, which is Kevin Bacon. The object would then be the River Wild, and then we would add a relationship between these 2 nodes, which would be the predicate. In this case, the predicate is that Kevin Bacon acted in the River Wild. Next, we would like to understand what the River Wild is. Now we know it's a film, so let's have a look at how we would model that. We begin with the subject, which this time is the River Wild. The object would now become film, and the predicate would be is a. This would give us a triple of the River Wild is a film. We will continue to add new items of information in this way, finding in this model that we can see that Kevin Bacon is an actor born in 1958 who acted in The River Wild, a film released in 1994. The beauty of the RDF is that we don't need to understand how any of the entities relate to one another before we ingest them. We simply need to add new nodes and relationships as we find them. We can then explore these relationships to discover new insights. The next type of graph database that we will look at is the labeled property graph, or LPG for short. In an LPG database, entities are represented by nodes and relationships as edges, exactly the same as the RDF. One of the big differences between the two is that the labeled property graph labels nodes and relationships, meaning that the type of each node is defined within the node itself. In our example from earlier, we could create a node of type actor that would look like this. The next difference between the RDF and LPG is that we can add properties directly to the nodes and edges in the form of key-value pairs. Returning to our example, this would look something like this. We now have a node of type actor that has two properties, a name, which is Kevin Bacon, and a year of birth, which is 1958. We would then do the same for the River Wild, this time adding a node of type film, and the properties of a title, which would be the River Wild, and the year of release, which would be 1994. With these two nodes now created, we can then add a relationship between the two, with a label of acted in. In addition to the label of the edge, we can also add properties to the relationship. Here we will add the character that Kevin played in the film, which was Wade. As you can see, the label property graph is conceptually easier than the resource description framework, but each has advantages and disadvantages. The RDF is primarily used within academics and research space, where the problems are less clearly defined. The labeled property graph is more commonly used in the tech industry. The type of graph database that we will use is the labeled property graph. This is because they're more readily available and easier to implement. The labeled property graph is defined by the Apache TinkerPop specification. This is an open source, vendor agnostic compute framework. Currently, there are over 27 implementations of the framework. The TinkerPop specification also specifies its own language called Gremlin. There are currently over 20 implementations of this Gremlin language. This is really similar to what we found happened with the ANSI SQL for standard, where none of the vendors have implemented a pure version of the standard. Rather, each vendor has implemented their own version. This is how we ended up with T-SQL for SQL Server and PLSQL for Oracle. So let's have a look at some of the actual implementations of the graph database that we're going to consider for our challenge. As this conference is primarily a SQL Server event, I thought I'd start by looking at SQL Server, which has an implementation of a graph database within it. In SQL Server, nodes and relationships are stored in tables. These tables are part of a schema that needs to be defined beforehand, and adding new types of relationships on the fly isn't practical. As someone who has worked with SQL Server for most of his professional life, this was tempting, but flexibility is one of the key features of a graph database, which SQL Server does not provide. So for this reason, I went looking for something else. Next, I looked at Neo4j. And Neo4j was probably the most popular graph database out there. It comes with this really handy desktop tool. Two things I really liked about Neo4j came with a really handy GUI that made working with and visualizing the graph really easy. Neo4j also implements its own graph traversal language called Cypher, and I found Cypher to be a lot more intuitive than Gremlin. The downside of Neo4j, however, was that the entire model needed to fit into memory. And as I was concerned about being able to run large memories on my laptop, I decided to look for something else. Finally, I decided to look at Cosmos DB. Cosmos DB is a multimodal database, meaning that it has multiple database engines running inside a single service. Some of these modes include things like document databases. One of the other services is the Gremlin API, which is a TinkerPop compliant service, meaning that we could use the Gremlin language. As a cloud service, Cosmos DB also provided a limitless scale at a relatively low cost. And this low cost included a free trial. So this is what I decided to use. Now that we've decided to go with Azure Cosmos DB, let's have a look at how it works. So Azure Cosmos DB is a globally distributed scale-out database that provides multiple database engines, which we call multimodal, within a single solution. In this slide, you can see that it supports a SQL API, document databases, column stores, as well as key-value databases. It's a turnkey, globally distributed solution, ultimately meaning you just click and it provisions itself. It's elastic scale, so we can distribute it both. We can scale up as well as distribute globally. It's also got fantastically low latencies with a 99th percentile and some great SLAs on that performance as well. Some of the features that Microsoft would like you to know about the Cosmos DB and the Gremlin API in general is the elastic scalability, throughput, and storage. So these are all adjustable, and on the fly, so you can really hit the right performance level for your application. There's multi-region replication, which really means that we can choose to distribute our workload to as many data centers across the globe as we wanted, keeping the data as close to our users as possible. It's a fully managed solution, which means that we don't need to worry about installing VMs, patching software, any of that ops stuff that we really want abstracted away from us. Cosmos DB also provides automatic indexing. This means that every property within the database is indexed, guaranteeing great performance. The Gremlin API also provides fast queries and traversals. It uses the Gremlin query to query it, and uses what's called index-free adjacency to find the next node. And what this really means is that the outgoing nodes are actually are embedded in the outgoing relationship, actually embedded in the nodes themselves. This means that there isn't a need for any sort of lookup to happen to find the next node. It has a memory pointer to that next node. So those lookups are incredibly fast. And finally, there's a tunable consistency levels, and this just really means that we can choose a strongly bound consistency level if we need it, all the way through to a eventual consistency level. So we've spoken a bit about Cosmos DB, but let's go and have a look at how this is actually implemented. To begin using Azure Cosmos DB, we're first going to head over to the Azure portal. Inside of the Azure portal, we're going to go and create a new resource. We can then search for the resource, or we can usually find it under the Popular Services option. We're then going to provide a number of details to set up our service. The first thing we're going to do is to select a subscription and a resource group. I already have a resource group existing. I've called Past Summer 2020. I'm then going to go and provide an account name. And this is the name of the service that we're going to provide. So I'm going to call it Pass Summit Demo. This name is validated first, so it needs to be unique across the entire service, as this is the URL that you're going to use to actually access the service. The next thing we're going to do is select an API. As mentioned earlier, there is a couple of APIs to choose from, such as the core SQL. We've got Azure Cosmos DB for MongoDB, so that'll be document databases, Cassandra, which is a tabular store, and then we've got Gremlin, which is the one that we want to go with. We then can choose a couple of options. There's a new notebook feature. I'm going to leave that off for now. And we really want to choose our location carefully. So you're going to want to place this service close to the services that are going to be consuming it. I'm going to leave it in US West, as that's where I've set up a VM that does my ETL load as well. New feature that's coming along is the ability to create a serverless version of the service. This is not available just yet, so we're going to stick with the provision throughput. The next option is to apply a free discount here. What this is that every subscription can create one Cosmos DB for free. But as you can see, I've already used the service, so I don't have the option of applying it to this. Okay, we're then going to choose an account type. I'm going to leave it as non-production. I'm also going to leave the geo-redundancy and multi-region rights as disabled. We can choose a couple of the other options, such as networking. This is relevant if we want to expose our service to the public internet or not. We can set up backup policies. We can set encryption keys. We can add tags if we like. And we're going to head on over to review and create. The first thing this is going to do is it's going to validate all our selections. Usually takes a minute or two, or perhaps not even that long, 10 seconds. And then it's going to, the first thing you can see is that it's going to tell us that it's going to take 15 minutes to create. So once we're done here, I'm going to pause this video and resume once the service is over. It's going to give you a high-level overview of all the options that we have selected, and then we're going to choose Create. Right, now that our graph is ready, let's go and explore it. So the first thing we're going to do is we're going to come to this overview page, and this gives us a high-level view and where we can perform a lot of actions. So we're going to be able to add graphs, we can delete the account, we can go to the Data Explorer, we can do a lot of these settings. Just a couple of things that we really want to pay attention to. The first thing is to grab these URIs. So these are the endpoints that we'll be able to connect to interact with our graph programmatically or using other third-party tools. We can also view graphs that we've created. And then we've got these sort of basic monitoring that will show you the number of requests coming into our service, as well as the estimated cost of the resources that we've used. A couple of features that we want to look at along the sort of control pane. The first one is probably replicate data globally, and this allows us to create copies of our data across the world. This is really useful if you have a global solution. Okay, we've also got default consistency, so you can set the consistency that you need. This becomes particularly relevant when you have this globally distributed system. We can go from a strong consistency level all the way through to eventual consistency. All right, so this is the strongest, something similar to what you might get out of a SQL database, all the way through to eventual, which pretty much means that eventually all the nodes will have the same data. We've got a backup and restore options, firewall settings, but we're just going to head over to this keys portion, and this is where we're going to get some of the access credentials that we need to interact with the service later. So again, here we can see the URIs. Okay, so we've got the .NET SDK as well as the Gremlin endpoint. Okay, we can see the primary key. This is something that you want to keep private. Don't worry, this database will be gone by the time you see this video. And here's the primary connection string. So this is essentially just all of these components pre-bundled into a single connection. Okay, with that said, let's go and create our first database. So I'm going to click on I'm going to head back to the Overview tab, and I'm going to click Add Graph. Okay, we're going to get this little pane to configure our graph. The first thing we're going to do is provide a database ID, and let's call this my first graph. Okay, the next option that we want to do is set the throughput level, and the throughput level is really the performance that you're going to get. The absolute minimum is 400, and it scales all the way to 100,000. And what a request unit is it's essentially the amount of effort required to move a 1K page. So at a very high level, we can perform 400 of these operations on those objects every second. We're also going to set the graph ID, let's call it my graph, and then the partition key. And the partition key is really only relevant to these globally distributed sort of solutions where we can distribute compute across multiple nodes, and we don't really have an appropriate key right now, so we're just going to choose the default one of PK, and we can click OK. And it can take about a minute for this database to get created. Okay, our database has now been created, so let's go and view some of the options. So we're going to expand the database that we've just created. And the first thing we're going to see is the my graph that we created, and then we're just going to go and view the scale. And this really allows us to dynamically change the size of this database. Not needed right now. Okay. Then we can also see the graph itself. Okay, so my graph, this is our graph. We can also adjust some of the settings. So if we need, and then view some of the stored procedures, user-defined functions and triggers, which we won't be looking at today. So let's head on over to the graph, and we've got, this is the sort of Graph Explorer, and we can load up the graph, and you can see that because we've just created this graph, we're not going to have anything Okay, so let's go and create a new vertices. So we've got this idea of create a new vertex. We're going to give it a label. So let's create a node of type person. And we've got the public keys already loaded. We're going to get into a default value of 1. And then we're going to go and add these key value pairs that we spoke about earlier. So let's go and create a key for name, and let's call that Mike. And it's going to add another one for age, and let's call that 39. Okay, so now we've got a very basic vertex that we want to add to our model. We're going to click OK. And here you can see we've now added that vertex to the model. It's gone and generated an automatic ID. Now we can assign an ID, and that's probably a good idea going forward. This would obviously be required to be unique. So, it's something you need to consider from your side. We can see the label, we can see the public key, as well as our 2 attributes that we created. You can also see any of the sources and targets, and really what this means is sources are there any relationships going out, and this is targets are there any nodes coming or relationships coming in. Now we've only got 1 node, so clearly we have no relationships, but as you can see, this is not a very practical way to interact with our graph. Instead, what we're going to do is we're going to use the Gremlin language. So before I show you that, we're just going to switch over back to the slides to do a more practical sort of introduction to the Gremlin language. Now that we've seen how to create a database, let's go see how we can interact with it using the Gremlin language. So Gremlin queries are what we call traversals, because ultimately in the graph database, that is what we're doing. Gremlin was also based on a functional language, and we call the functions within Gremlin steps. Each step processes the results and then passes that to the next step after it. So how this might look is we might have our first step that would do some amount of work, whether that was returning things or filtering items, whatever that would be. It would then pass that through to the next step. That step would again provide some functionality. I would pass that to the next step and the next step, and that's how we would get work done essentially with our traversals. Now, the steps that we have in Gremlin can be grouped into a couple of areas. We have transformations, and transformations generally mean that we're going to move around in the graph. Then we've got filter functions, so very similar to the where clause in SQL, where we're going to go and sort of selectively remove items. And then we've got side effects, where we essentially modify the state of the graph or the result set. So let's go and have a look at how that works practically. All Gremlin commands begin with a reference to the graph itself, and that's just simply denoted by a G. Okay, so we're going to begin by taking this reference to the graph, and then we're going to pass that to our first step. And the simplest one is really just a capital V. And what this means is that we're going to go to our graph and we're going to get a reference to each and every vertices or node within the model. Okay, so when we run this command, it'll return all nodes. Now this could be a huge result set based on the size of the graph. So now think select star from, right? Okay, so we want to be careful with it. We can be a lot more selective with our queries. Let's begin with this. What we can do is we can hand an ID as a parameter through to the V function or the V step, and this will return a vertex based on an ID. So if we know the ID of the graph or the ID of the node, we can filter on that. We don't always know the ID, and sometimes we want to return on something more broad than that, and for that we have the has function. And the has function is very similar to the where. What we're essentially saying here is go and return all of the vertices within the graph and then filter them where the name is equal to John Smith. And this would return all nodes where the name is John Smith. Next thing we might want to do is try to get an understanding of how many nodes we have in our graph. So for that we have the count function. So in this example we're going to return all nodes within the graph and we're going to go and count them. This will return an integer. But sometimes we want to be slightly more selective. Counting all nodes might not be all that useful. So we can combine some of the functions that we've already seen. Here's another filter function called hasLabel.
So instead of filtering based on a property, what we're doing is we're filtering based on the label itself. So here we have a model where we have vertices that are of type person, so we are starting with all vertices, getting only the persons out of it, and then we're counting those. And that'll give us a count of all the person nodes within our graph. The next thing we might want to do is, instead of counting a specific value, what we want to do is be able to do what you might think of as a group by in SQL. So this is an example of doing exactly that. What we're doing here, again, we're returning all the nodes in the graph. We are then extracting the label. Okay, so we're not emitting, this step is not going to emit nodes, but strings. Okay, so for each label, it will emit the label description, and then it'll pass that through to the group count. And what that'll do is that'll then count the number of the occurrences of each label type within our model. Now, what we've done till now is basic select statements. We also want to be able to modify the state of our graph. Very similar to SQL, so we have the CRUD operations, so we can go and create, update, and delete. So let's have a look at how that happens. The first thing we're going to do is add a node, and we can do that with the add v. So this is add vertex. And what I'm doing is I'm adding a vertex with the label person. Now this isn't a very useful node because it has no identifiers. It's just going to be this virtually empty node, useless. So what we really want to be able to do is add additional properties, because this is a property graph, right? So we're going to do that through the use of this property tag. So what's happening here is we're adding a vertex of type person, and then this function or step is emitting the newly created node, and this property function is then adding or updating the value where the key is name, and then the value would be Harvey Keitel. That in turn is passed again to the property function, where we add a year of birth function, where we put 1939. And we can go and add as many properties as we need to this item. Now, just a heads up, one of the things that we're going to see in Cosmos DB is that Cosmos DB uses this notion of a partition key, so we need to provide that partition key to the queries as well. Next thing we want to do is go and create a relationship between two nodes. And before we can do that, we need to get references to our two nodes. And that really starts here. The first line is we're going to go and create a relationship from the node called Bruce Willis to the node called Pulp Fiction. Now, all relationships traverse from a node to another node. So what we begin by doing is finding a reference to the Bruce Willis node, and then to that node we are going to add an edge. Okay, we're going to give a label to this newly created edge, acted in. But in order to create an edge, we need to know where it's going. So we specify the to step, and then we're going to, within that step, requires a parameter, and that parameter is going to be the node that we're going to return. So again here, we're going to search all our nodes where the label is film and the name is Pulp Fiction. This is then going to go and create a relationship between our Bruce Willis and our Pulp Fiction node, and then what we're going to do is we're going to go and add a property to that. So we're going to say add a property for the character and call it Butch. All right, so we've done a very simple insert. We've also done essentially what are updates. Next thing we might want to do is delete. So, and we can do that very simply with the drop statement. Now, what this statement is doing is it's saying, go and get me all of the vertices, so all the nodes within my model, and drop them. Okay, so essentially almost like a truncate statement, right? We're going to drop everything. Not recommended for production. Okay, so now that we understand some of the basic Gremlin commands, let's have a look at what traversals are within a graph. And we're going to create a very simple path, okay? And paths, or a simple graph, and graphs have paths. So a path is the walk between one node and any other node, okay? So in this case, we have two paths. We can go from node A to B to C to D, or we can go from A to C to D. Okay, so those are the two paths that we have between A and D. Okay. Next up, we want to basically be able to traverse some item. So the first thing we're going to do is we're going to go and get a reference to the vertices with an ID of C. So that's this guy right over here. And then we're going to use this function over here, this traversal step called outE. And what that means is go and find all of the edges that are coming out of this node. So you can see that this node actually has 3 edges, but 2 of these are coming into it. They're coming from this node into this one. And remember we spoke about directional relationships, and this is where that comes in. So we're coming from here to here. But in this case, we're going to say, give me node C and tell me all of the edges that are leaving it. So we have a reference to this relationship. Okay, note, not the node. Now, if we wanted a relationship to the node, what we could do is we could say, go and give me the vertices C, go and get me all the edges that are going out, and so this has a reference to this relationship again, and then go and tell me all the vertices, okay, and a single relationship can only have one, okay, go and tell me the vertices that this is going into. So that returns me the label or the node D. Right. We might want to be a little bit more generic. Okay, so instead what I'm going to say is, what I'm interested in is go and find me the node, again node C, but I'm not concerned about the direction, so I'm going to use the both command. I'm also not interested in this time is going to first to the relationship and then to the node. I can move directly to the nodes that's around it. So both is say ignore the relationship and bring me that vertices. As you can see here, we're going to return all 3 nodes. All right, so let's go and have a practical look of how that might look in a very simple model a simple version of the model that we're going to build in a second. So here we are back in the database that we created earlier. You remember my first graph, and now I've already pre-populated a couple of nodes. So let's quickly go have a look at what that looks like. I can either run my g.v, remember what that'll do is it goes and returns all my vertices within the model, or I can click on this load graph option over here. That's going to run quickly, and this has returned a couple of the nodes that I've created. So we've selected a couple of actors as well as a couple of forms, and we're going to load them in. But before we get to that, what I want to do is have a look at how we can go and create the queries. So to begin with, what I want to do is I'm going to go and add a new query. We're going to go and add a new vertices. We're going to make it of type person, okay, and then we're going to assign a property named Bruce Willis, okay. And then, as I mentioned earlier, because this is Cosmos DB, we require a partition key. So we specify the partition key. It's not particularly useful like this. These are all hard-coded, but this is a very small data set. So the partition key is not required. So what I can now do is I can go and add this node called Bruce Willis. You'll notice there is no Bruce Willis in here. I'm going to go and add it to the node. So we're going to go and execute that, and you can see that a new node is being created. Remember, what's happened here is that these steps have emitted a new node, which is why I see it here. I don't see all the nodes because I haven't queried them yet. But let's go and do that. I can go back to G. Let's go and call all the vertices. And this time you'll see that Bruce Willis is now amongst them. Okay. Now, the next thing we want to do is go and add relationships. And you can already see that's happening here with Samuel L. Jackson. We want to go and create that relationship between Bruce Willis and the Pulp Fiction movie. So we're quickly going to go and bring in the query. We're going to say, go and grab me the node from Bruce Willis, add an edge for acted in, okay, and then we're going to go specify a link to the Pulp Fiction film, and then we're going to go and add that property Butch, okay, for the character name. Okay, so let's quickly run that. And we've now returned an edge. And you'll notice because we're returning an edge, the visualizer can't actually visualize an edge, so you essentially just get the JSON result set out. Okay, not a problem. Let's go have a look at what our result set looks like, so we can execute our gremlin again. we're going to go to the Bruce Willis node, and you can see that the Bruce Willis has an outgoing node to Pulp Fiction. Okay, very simply through the browser here, you can see that we have an outgoing edge with the label acted in for Pulp Fiction. Okay, so that's sort of some very basic CRUD commands. Let's go and have a look at some of the, let's go and explore our model a bit. First thing we want to do is really go and count all of these nodes. So we're going to begin with counting all the nodes, and this is going to return us a number this time. And this is the JSON result set that we'll get out. So how many edges are there? Well, there's 7 in there. We can also go and count the edges. So instead, if I'm not interested in the actual vertices, I'm more interested in how many relationships there are. We can run that, and we can see that there are 6 relationships in the model at the moment. Next thing we want to do is let's go and count how many of those nodes that we saw earlier are actually people. So again, we're going to go and get all the nodes, but we're going to filter for persons, or for person. And we can see that there are 5 people. We can do exactly the same thing. What I'm going to do is I'm going to go and count, but not where the label is person. I'd like to understand how many of each type of label do we have in the graph. So we're going to use our label command, which is going to emit the label as a text, and then we're going to group by that amount. So when we run that, we can see, well, there are 5 person nodes and 2 form nodes. Okay. Next thing we want to do is go and look at some of the filter functions. So what I'm going to do is I'm going to search the entire graph for a person that has a name of Uma Thurman. So this is going to return me a node. So that is the node that we expect to see. And you can see this node has 2 outgoing relationships that will link to Kill Bill and Pulp Fiction. All right, but let's go and have a look. I'm less interested in the node itself. So perhaps I'm not interested in Uma Thurman and her properties. What I just want to actually understand is what nodes, in our case, movies, did Uma Thurman sort of act in. Okay. Now we're provided no sort of context to that, so we just know that actors can only link up to movies. Okay, so when we run this command, you can see that we have it's emitted 2 nodes, one of Pulp Fiction and one of Kill Bill Volume 1. Okay, so now we've emitted 2 nodes, but perhaps we don't actually want the nodes themselves. We want to return something closer to a tabular result set that we get in a within SQL. So what we can do is we can then go and specify, don't return me the nodes, rather go and pull out the properties of type name and return those. So I'm going to run that, and here we get a basic JSON set that says, well, Uma Thurman has acted in Pulp Fiction and Kill Bill. All right, so that sort of concludes our sort of simple introduction to graph databases. I hope you can see how we can explore the model. If we wanted to just play around with it for one more second, if we come into this view, I'm going to go pull up all the nodes. I can start with a node and I can sort of expand. Now this is a function of the sort of data explorer itself. So we can do this. I mentioned earlier that I kind of like Neo4j. It has a nicer user interface when it comes to these sort of things, but you can see how we can sort of browse through the graph. So find Uma Thurman, we can find Kill Bill, we can expand, we can find actors. So you can kind of see how we can build up this graph that we can explore. All right, so that's the foundations of what we're going to use to solve our problem. Next thing we're going to do is actually look at how I populated the graph database with the IMDb data. The next thing we want to do is import or go and load the data set that we're going to use to solve our problem. Now, I began by looking for data sets with all the movies and actors, and IMDb is a fantastic reference to that. So for those of you who don't know IMDb, the Internet Movie Database, basically every movie, every actor, it has a whole bunch of sets. And what they have is a extract of all of their data sets. So here we can see that we've got data sets that are all tab separated values. We have lists of all the films. This would include things like a unique name for the film, the title that it was released with, as well as the sort of original title. It'll tell you if it's an adult film, the year it was released, the year it ended if it was a TV series, the runtime, as well as any genres that it might be part of. So we've got data sets for the movies themselves, as well as the actors. Now, one of the shortcomings of this data set is it's not actually a complete data set. It only lists the principal actors within a film. So that means when I'm going to go and calculate the Baker number, it's actually not going to be all that accurate, because it wouldn't include the sort of minor actors in a role, which obviously could create shorter paths through our model. But unfortunately, it is what it is. So let's go have a look at how we're going to do it. So I downloaded these extracts, and they look something like this. So this is the films. So you can see it generates a unique key for each short. Tells us what type it is. So is it a short? Is it a movie? Is it a TV series? We can then see the name of the film. We can also get the release year, as well as things like the genre. And we're not going to import all of this data. We're obviously going to be somewhat selective. Now, how did I go about this? We're definitely not going to do it the way you've seen me just a moment ago. We can't sit and copy and paste commands into terminal. Instead, what we want to do is enable programmatic access. And for that, Cosmos DB has a .NET sort of library that allows us to interact with the Cosmos database in an efficient manner. So the first thing I did was obviously head on over to docs.microsoft.com, and it has the sort of Azure Cosmos DB database Gremlin API. So we can install this, we can create a new console app, and we can install this. So that's exactly what I did. I went and created a basic console app, still called Hello World, specified a few resources. So I've got the sort of URL of the service. I've got the primary key, that's that link that I showed you earlier, as well as the name of the database and the graph. All right. Then I went and created a function. In this example, it loads up the actors. And what this does is it goes and connects to that file, so that file that we were looking at a minute ago. It then goes and opens a stream reader, and you'll notice I'm not a C# developer. Okay, so once we'll create a stream reader, and this allows us to read through the file. And then what we can do is we can then go and say, for each line in the file, go and perform some function. So before we start iterating to the file, we basically create a connection to the Gremlin server. We set up a couple of our connection properties, and then we go and set up the Gremlin client. And this is what actually facilitates all of the work. Okay, so with that connection now out of the way, we're going to go and create that loop. So this is that file. So it'll read each line within the file. And then I went and used a string tokenizer. So basically what it does is it goes and grabs the first line, it splits it based on that tab, because remember this is a tab separated value. The first item is the actor ID, the second item is the name, and the third item is the year of birth. So we're going to go and pull those three attributes out of the text file, and then we're going to generate a query. So exactly like we've done earlier, we're going to say go and add a vertex to my graph of the label type person. We're going to add a ID, okay, and we're going to make that the actor ID. We're going to create another property of name. We're going to add the actor's name, and then we're going to go and add the year of birth. And because this is Cosmos DB, we require a partition key, so I also added the partition key. Okay, so I went and ran this, and it ran somewhat efficiently. I was inserting on a single thread about 100 items per second. This is generally how you would go about building applications to insert data. Now this wasn't very efficient, because although 100 items is great, I needed to import 10 million actors, okay, which means that this process would probably be running for a couple of days, so I really needed a new solution, right? And for that, Gremlin also has a bulk bulk operation library where we can import sort of bulk items similar to how BCP might work in SQL. Okay, so I went to the site. It has a sample library. So on GitHub, there's a Visual Studio solution that you can pull. I went and pulled that down, and I had to modify it somewhat. Right, so we've got the basic settings. They've got a config file here. I would put things like my endpoint, my key, and then a couple of other details. The database name. I can set the throughput. I set it to 40,000. So remember, the lowest is 400. The highest is 100,000. I obviously needed it to be rather large, so I could ingest these values. Okay. With those sort of basic config settings done, I found these functions over here, which is what it uses to import the data. And what it does is it creates an IEnumerable list. Okay, so this is just something that can be traversed over, and then it inserts all of these items. So this is in the utility function. I'm just going to go and browse to that. You can see here that we've got this bulk extractor. So I want to go. That's the one I want to find. Okay, so what this will do is exactly like we did earlier. What I'm going to do is I'm going to open a stream reader. Okay, so I pass the file name in there. I create a stream reader, and I loop over each line in the file. I pull out the actor, the name, and the year of birth, exactly like I did in the last application. And then I'm going to add these commands. So you can see that we can actually add a new vertex. We can give it the ID. We can give it the label. We can then add properties to this, and then we can add that new vertex to this IEnumerable collection. It then hands that entire collection up to the service. So instead of making a single call at a time, it actually loads all of them up. And I got good speeds through this, so I was inserting at more than 2,000 records per second using this approach as opposed to the 100. Well, it's like a 20-time increase. Now, a couple of things I didn't do is I haven't really used the partition key. I would have probably seen much better performance enhancements had I done that. Okay, so that's how I loaded the data. For our final demo, we're going to look at finding the shortest path, or in our case, really that is the Baker number. So let's see how we would do that. I'm going to come straight to the query. That's a little bit complex, so let's break that down a little bit. First thing I'm going to do is we want to find Kevin. Now, Kevin's ID in the IMDb database is NM0000102. Okay, so we begin by finding that path to Kevin Bacon. Next thing we want to do is we want to go and find that node that we have, and we want to branch out. And we know we can use the both statement to do that, because the both statement takes a node, all right, and it then goes and finds all nodes at the other end of a relationship. Now, this relationship could be in or out. It's important we do it this way, as you'll see in a sec. So once we've chosen that both, we then use the simple path, and this basically reduces the paths to ensure that we don't have sort of repeated paths coming in. And that's because the next thing we're going to do is we're going to repeat this process of starting at Kevin Bacon, branching out to all the movies that he's acted in. Then this both statement is executed again, so it'll go and find all the actors that have acted in movies that Kevin Bacon has acted in. So this returns a much larger set. And this process is going to repeat until we have a condition, and that condition is the person that we're looking for. So in this case, we're looking for Meryl Streep. So it'll expand out until we found that Meryl Streep item. And then the thing we want to do is we want to go and return the path that comes from Meryl Streep to Kevin Bacon. So let's have a look at how that runs within Cosmos DB. Right, here we are back in Cosmos DB, and let's have a look at how we can find the shortest graph. First thing we're going to do is we're going to start by beginning at Kevin Bacon. So this is essentially the lookup for Kevin Bacon. We can see that there he is. Now, one of the things we're going to do is we're going to load up this search path, And we're going to run that query that we just spoke about. So we're going to continually radiate out. We're going to repeat that until we find Meryl Streep, and then we're going to return the path. So let's see what this does. So we're going to execute that query, and we can see that it has returned an object. Okay, so this is a path, not a node, so we don't get the visualization, but we can see that there are a couple of objects in here. So the first, we start off at this node, which is Kevin Bacon. And Kevin Bacon is then, we then go down this path from Kevin Bacon to the River Wild. And then from the River Wild, we can see that we come out at Meryl Streep. So this object describes that path from Kevin Bacon through to Meryl Streep. Let's do the next one now, which is Ian McKellen. If you remember, that has an Ian McKellen had a Bacon number of 2. So again, we can see that we have a starting point of Kevin Bacon. We're then going to head on through to X-Men Days of Future Past. And then in X-Men Future Past, Michael Fassbender also acted. Michael Fassbender acted both in X-Men Days of Future Past as well as X-Men First Class, and Ian McKellen acted in the First Class movie. So this sort of completes the path that we were looking at. So now we can see how use these paths to determine the shortest path between any two actors. And that concludes my talk today. I want to thank you for joining me, and I hope you found graph databases really interesting. You should really consider having a look at them. They can help us solve a lot of new kind of problems. If you'd have any questions for me, I will be online shortly. Thanks a lot. Cheers. Bye.